How do we reverse entropy and stop the universe from dying? To understand how important this question is, imagine what the end of the universe will look like. The universe is tending to greater disorder because of the second law of thermodynamics. Entropy, a measure of disorder, always increases. Disorder includes not only messiness, but a tendency for things to spread out and decay. While the universe appears to have started with a bang, it will end with a whimper. Currently, within the timeline of the history of the universe from birth to death, we live in the Stelliferous era. This era begins with an event called recombination, the formation of the first neutrally charged atoms. The cosmic microwave background, the background of radiation that constitutes the earliest light we can see, appeared at this time a few 100,000 years after the Big Bang. Before recombination was the primordial era, a time when stars could not form and the universe was a dense, hot mass of plasma. The first stars began to shine much later when the universe was about 100 million years old, and the first galaxies formed at about 600 million years. The Stelliferous era will continue until the universe is about 100 trillion years old, according to projections. At that point, there will no longer be any fuel left in the universe, and the universe will enter its dark ages. The stars, one by one, will start going out. Our own sun will become a black dwarf, a stellar mass body so old that none yet exist within the universe. By 1 quadrillion years old, the universe will no longer have solar systems. All planets will either be flung out of orbit or consumed. Galaxies will degenerate, losing all their stars to black holes, or into the depths of intergalactic space. By 10 quadrillion years, all of the matter in the universe will have decayed into stray photons. Matter as we know it will no longer exist. The only massive bodies left at this point will be black holes, which decay slowly by releasing Hawking radiation. After about 1 googol years, 10 to the power 100, all these black holes will have decayed into nothing. At this point, the universe will be essentially blank, with little but photons and neutrinos, which will redshift to lower and lower energy as the universe continues to expand. The human species is unlikely to survive even a small fraction of this time, but setting that aside, is there anything that we could do to stop the relentless march of entropy? The key to restarting the universe is bringing matter back together or making new matter from nothing. To this end, in 1992, Lee Smolin proposed his evolutionary theory of universe generation. He presupposed that universes can beget new ones, and if they can, then they would follow the same rules of natural selection that living things do. The universes that produce more universes that survive and produce more would persist, conferring their physical laws and structure onto future universes in some kind of DNA-like encoding that we would experience as the laws of physics. This idea solves an important problem in cosmology and the foundations of physics called the fine-tuning problem. Fine-tuning is the concept that, for some reason, the universe seems specially tuned to produce things like stable matter that leads to human beings, rather than just appeal to the anthropic principle that we live in that kind of universe because we are here. The mechanism by which universes produce new ones is through the formation of black holes. A black hole, like a universe, contains a singularity, or at least a tightly bound ball of matter and energy. I'm going to call it a singularity for simplicity. The difference is that a universe begins with a Big Bang singularity in time, whereas a black hole contains a singularity in space. That turns out not to be a problem, however, because when matter falls into a black hole, its time dimension, the direction in which it experiences time flowing, gradually bends towards the singularity, so that when it reaches the singularity, its time dimension is directly into it. If a universe is on the other side of a black hole singularity, then the matter that fell in would simply emerge at the Big Bang of a new universe. During its fall into the singularity, of course, it would become thoroughly mixed up with other matter falling in, and any information it contains might be erased or so thoroughly scrambled as to be irretrievable. So don't think of sending any messages. The black hole Big Bang theory solves several problems in cosmology. It solves the horizon problem, which is the problem we see in the cosmic microwave background, in which different parts of the radiation from the night sky are too correlated to have happened after the universe began. The current reigning theory for explaining this is inflationary theory. The black hole Big Bang theory is also inflationary because the space-time called de Sitter space that connects a universe to a black hole singularity is inflationary in its initial stages. But some of the mixing that explains the horizon problem occurs while the matter is falling into the black hole in the mother universe. It also solves the flatness problem, which is probably more important. Inflationary theory alone has a lot of fine-tuning problems of its own, which is why we get completely unsubstantiated theories like eternal inflation. The flatness problem asks why the universe appears to be perfectly flat spatially. Astrophysicists explain that with dark energy, but the black hole Big Bang theory explains it purely from the topological requirements of connecting a universe to a black hole singularity. Only a spatially flat universe will do. Thus, dark energy would not even exist in this model. It comes down instead to the way mother universes give birth to baby universes, sort of like how human babies have flexible skulls so they can fit through a birth canal. If you didn't know about birth canals, you might be confused about why babies have squishy, fragmented skulls. Smolin argues that our universe is specially tuned to produce black holes and that small changes in the constants of physics would not allow for such prolific generation. That means that if universes do arise out of black holes, our universe is, as we speak, generating baby universes constantly. One question is, if all these black holes contain stellar mass amounts of matter and energy, how can they form new universes? Wouldn't they just form small ones, not like our own with billions of galaxies? Potentially they would not, because of the way that time and space switch places within a black hole. Any matter falling into a black hole will emerge at the Big Bang of the baby universe. No matter when it falls in during the life of the mother universe, it will emerge at different spatial locations in the new universe, but all at the same time. So the Big Bang is spatially compressed, like a black hole from the point of view of the mother universe, but temporally compressed from the point of view of the baby universe. Likewise, it will be temporally extensive in the mother universe, but spatially extensive in the baby universe. That means that all the matter that will ever fall into the black hole will contribute to the new universe, not just the initial star. That is more matter, of course, but hardly a universe full of matter. Until we consider that there is another source of contribution, space-time itself. Consider a thought experiment. Suppose you have a string that is 1 billion light-years long and you connect it to anchors on 2 planets in distant galaxies. As the universe expands, the string will gain tension, which is useful potential energy. This is a general feature of the universe. Its expansion generates anti-gravity or tension in space-time, which creates energy out of nothing. The conservation of energy is violated here because general relativity doesn't conserve energy at cosmological scales. Energy conservation is a result of time translation symmetry, the idea that physical outcomes don't change depending on when they happen. Since the universe has a beginning and a definite way it unfolds in its expansion, every interval in time is not precisely interchangeable with every other interval. Hence, the expansion of the universe creates energy at large scales, but not very much. When the universe expands very rapidly, however, much faster than the speed of light, then you can create a lot of matter out of nothing by throwing negative energy past the Hubble sphere. This is the separator between space expanding slower than light and space expanding faster than light relative to your location. Ejecting negative energy causes the density of vacuum energy outside your Hubble sphere to reduce, and you get free matter and energy in exchange. Physicist Paul Davies explored energy and matter generation in his paper Mining the Universe, in which he considered how one could extract unlimited energy from an inflating universe. He notes that the inflationary phase of the universe, the de Sitter space, produces Hawking radiation in the same way that black holes do. This Hawking radiation is essentially free energy. This is how standard inflationary theory explains the appearance of the universe in the first place. But when you connect it to a black hole in a mother universe, you get a much more complete picture. The de Sitter space that connects the baby universe to the black hole in the mother universe produces enormous quantities of matter and energy from nothing. That production mostly ceases when it returns to ordinary expansion. This is why a black hole, formed from a mere stellar mass, can create a whole universe of galaxies. According to recent estimates, billions of these black hole portals to other universes could be scattered throughout the cosmos. Going back to the problem of the last question, is there a role for intelligent life in restarting the universe? It seems that the universe and its predecessors have already solved this problem. Time ceases to mean anything when talking about universes producing new ones. But certainly you can talk about a long line, perhaps an infinite line, of universes that learned or evolved how to produce new ones. To enter another universe, you would simply have to jump into a black hole. This would kill you, of course, but your matter would be recycled into the new universe. You might ask whether we could restart this universe over again. In order for that to happen, this universe would have to enter an inflationary phase where it produces fresh matter and energy. If a species were smart enough to manipulate the gravitational behavior of an entire universe, then it might be physically possible. Such an inflationary phase would effectively create a bubble universe inside the old universe. But probably the best way to do that would be to make a black hole. Hence, we are back to the solution that our universe's predecessors already discovered. This goes to show that far from needing to merge with some god computer in the distant future, we are actually the products of a universe endowed with a godlike power, one that may countless times be saying, "Let there be light." And each time a black hole forms, there is light. Thank you so much for coming this far with us. See you soon again, the next day, in the next video. Until then, good night.